Okay, everyone. Good morning, good afternoon, good evening, everyone. We are Veloce Hyperloop from IIT Bombay, India. Myself, Shashank, Propulsion Subsystem Head, and I'll be presenting the Propulsion deck on behalf of Veloce Hyperloop. So, the presentation is divided into three parts. We start with talking about the induction motor, its construction and working, followed by the linear induction motor, its corresponding construction and working, and dwelling into our own model of the LIM. Further, we'll be explaining about the 2D magnetic analysis which we did, and we'll be explaining the results we got in the form of the graphs. So let's have a look into the induction motor. So the induction motor works on the principle of rotating magnetic field. We will look at both the geometrical and electrical perspectives. Geometrically, it is made up of two parts, stator and rotor. Stator, as the name suggests, is the stationary part of the motor, which is made up of electrical grade steel laminations, and slots are cut into them. Furthermore, copper wires are wound on the teeth in a specific formation which is powered by a three-phase supply. The secondary part is the rotor, which consists of conductive materials shorted by end rings. Now we'll look at the operation of an induction motor. So powering up the three coils with a three-phase supply leads to generation of a rotating magnetic field. The speed at which it rotates is called as the synchronous speed. We'll have a look at this rotating magnetic field in the next slide. The operation will be basically once a rotating magnetic field is generated, the flux lines cut the rotor conductor, which induces current in it. This induced current creates its own magnetic field, which tries to catch up with the stator magnetic field. And due to this phenomenon, the force acts on the rotor and it starts rotating. However, its speed will always be less than the synchronous speed. Now, let's have a closer look at the rotating magnetic field. We will be having three phases. As you can see in the picture, the three phases are once marked in blue, green, and red. All of these three phases are sinusoid in nature, where each of them differ by a phase difference of 120 degrees. This phase difference accounts for the peaking of the sinusoids independently. One thing to keep in mind is that these sinusoids sweep in time. However, at any instant, the vector addition of these three phases gives rise to a sinusoid of higher amplitude. However, this one sweeps through space. Hence, it is called as a rotating stator field. Now, we are done with the basic talk about the induction motor. Now we'll look how we sort of incorporate the induction motor phenomenons in the LIM. So we'll be basically starting with the construction. The LIM also works on the similar principle as that of an induction motor. The picture on the right shows the transformation from an induction motor to a linear induction motor, which is possible by cutting along one of the radii and laying it out flat. Multiple such flat portions are connected end to end with each other to create an infinite LIM. However, one thing to note is that the name of the stator and the rotor interchange among themselves in case of LIM. The pod, the pod, which is the stator, which carries the core and the powered windings, is the one which travels, and the rotor and the conductive materials which form the rotor are stationary. Okay, and now we'll be venturing into the linear induction model of ours. So we as a team decided to hand ourselves this job of making an LIM. So we cornered upon ourselves on a 12 slot 4-pole 3-phase powered LIM, as we had an intention of creating a powerful yet a compact LIM. The geometrical constraints for this LIM stand at 44.5 centimeter lengthwise and 17.5 centimeter in the breadthwise. So this is quite compact in nature. Electrically, we would be powering it with a current supply of 100 amps, and the number of turn of the coils is fixed at 35. The synchronous velocity turns out to be stationed at 22.25 meter per second. Now, since we have the model of our LIM ready, the 2D magnetic analysis will be performed. So the 2D magnetic analysis was performed and the results were plotted for further analysis. we chose COMSOL as our preferred software for simulations. Now, frequency was one of the independent parameters available to us, so we used it to manipulate the results according to our needs, and we will be further using it. So the magnetic field analysis was performed and the frequency dependent study was triggered. The obtained results were plotted, which were namely thrust versus velocity plots followed by thrust versus frequency. So this is the COMSOL simulation which we actually did. Now what you are looking on the picture, at the picture on the right hand side, is the magnetic flux density plot along with the magnetic field lines for RLIM. The color bar on the extreme right shows us the flux density in Teslas. A close look at the flux density. The flux density in the stator base stands at 0.5 Teslas. However, the flux densities along the tooth stand roughly in the range of 1.5 to 2 Tesla. Hence, overall, the average flux density for the LIM lies in the region of 1.5 Tesla. However, since this is a 2D analysis, we have chosen a specific thickness. If we want to decrease the flux density at any point, we can increase the thickness or increase the number of laminations. It can be suited accordingly. If we have a closer look at the magnetic field lines, you can see 4 loops forming. I can highlight the 4 loops. So basically this indicates that this is a 4-pole motor. Also, we are having minimum leakage flux. However, the leakage flux on either side is due to the end effects. Now we'll be looking at the thrust versus velocity plots for multiple frequencies. This graph consists of frequencies ranging from 0 to 100 Hz at a step size of 5 Hz. If we look at a general plot of either of the frequencies, the curves show an increasing value of thrust, they hit a peak and they keep on decreasing thereafter. Hence, a curve gets divided into 2 parts on either side of the peak. So the one on the right side of the peak is called as the equilibrium region, whereas one on the left side of the peak is called as an unequilibrium region. So the reason being, if so the reason being the one on the right side of the peak, if due to any kind of external factors, if for some reason if the velocity increases, then correspondingly there is a decrease in thrust. Hence we get back to the stable point. Similarly, if due to some reason if the velocity is decreased, there is a corresponding increase in thrust and we will be again reaching our desired velocity. However, same cannot be said for the region on the left side of the peak, because a corresponding increase in unwanted velocity leads to increase in thrust, which gives rise to instability. However, since the motive of our LIM is to keep on increasing the speed as we move on, so we'll be following a method called as frequency jumping. So basically we'll be, for having a constant acceleration, we'll be jumping between the frequency curves so that higher and higher speeds can be achieved. And since frequency is one of the parameters which we are going to control, hence a use of variable frequency generator helps us to succeed at this task. There is one thing to be noted, that for the lower velocities, the frequency jumping will be lesser compared to that in the higher region, because as we approach the synchronous speed, the frequency curves get closer to each other. Hence, the frequency switching for a small range of velocity will be higher. However, a closer look tells us that we won't be able to ever reach 22.25 meter per second speed, which is the synchronous speed, and which is correct considering that we are using an induction motor. So the maximum speed which can be achieved is roughly tapped to be around 21 to 21.5 meter per second. We have this another plot. This plot is of thrust versus frequency for different velocities. Just a spoiler alert, this graph is not important from the perspective of LIM. However, it is quite important for variable loading. In a nutshell, the region towards the left side of the peak is a stable one, whereas the region towards the right side of the peak is an unstable one. However, since most of the load during a pod transit will be roughly constant, the impact of this graph is almost negligible. Since we looked at both of the graphs are completely independent of each other and serve different requirements. And based on the kind of work, we can use them accordingly. However, right now we are in the process of figuring out the relation between, we are figuring out the thrust, we are trying to figure out the thrust, which can be a function of both frequency and velocity. Once we are able to get out that result, we'll be completely done with the 2D magnetic analysis. Okay, now since we are dealing with high currents and high voltage, it raises a serious issue about the safety of the pod. Hence, we did a failure mode, hence we penned down a failure mode element analysis, and we can actually look at the different kinds of the failures, their corresponding cause, how can we detect them so that we can avoid them in the near future, and how the system actually responds to these kind of the failures. So since our LIM consists just of the iron core and the copper wire, so these are the major hotspots where we can actually incur some of the failures, and they are listed right here. So our further plans will be, as I said, we are almost done with the magnetic analysis. We'll be venturing into thermal analysis to figure out the hotspots and then prevent any kind of and ensure that we are having zero failure. Then we'll be venturing into the manufacturing, followed by conducting trials and testing of our prototype. Thank you.